Hello, we're back again and we're going to be looking at stresses today. So hopefully this is a refresher for mechanics and materials. You should be able to go back over your notes in that class and remember how we find these stresses and how we find principal stresses. But for the purposes of getting us all on board with the same thing, this video should be a quick reminder.
Now, of course, most parts experience more than just one type of loading. In fact, they're often loaded with multiple types, and so we'll deal with how to combine those in just a moment. But assume we've got some part, and I'll just draw a rectangular prism here. We can put it under some bending moment, M. We can put it under some torsion, some torque. T. We can have some axial load P, and all of that will lead to some amount of stress throughout the part. And of course, we'll want to know where on that part the stress is. So failure always occurs at a location, and so we will need to be very specific about where we're talking about location. For axial stress, the stress tends to be constant throughout the part. Bending stress tends to be maximum at a location, and torsion tends to be fairly constant along the outside surface. So we're going to need to pick a point that likely has the worst amount of stress from all of the different types of loading. And we call this our stress element. That's our point, and we imagine it as some infinitesimally small block that has some loading. And we can say there is stress acting, let's use an XYZ coordinate system, on the X face acting in the X direction we call, normal to the X direction, we'll call sigma X. Sigma Y is the same, except acting on the Y face in the Y direction, equal and opposite, since we're starting with a statics assumption here that this part isn't, the elements of this part aren't moving around inside of it. We will have in the negative X face, the negative X direction. All right, so that's the normal stress, but we also have shear stress. So acting in the X face in the Y direction, we have that stress XY. Acting on the Y face in the X direction would be tau YX. And same thing on the opposite side. So what we end up with is a stress state. This is a 2D stress state. That looks like this. Acting in the X direction, let me say direction on this side and face on this side. Acting in the X direction on the X face is sigma X. Acting in the Y direction on the Y face is sigma Y. Acting on the Y face in the X direction and acting on the X face in the Y direction. So that is a 2D stress state. Now, for a moment, we can consider that we need, in this 2Ds, we need 4 different stress values. But for a moment, we're going to realize that these two must actually be the same thing. So consider for a moment a stress element where we just have sigma, what would be the xy here, or tau xy. That is shear stress acting on it. Would this block be spinning around as it's drawn here? Yeah, it would, right? If we put a force on one side, put a force on this side, there's no statics to hold it steady. So there must be some equal and opposite reaction keeping this little stress element from spinning around inside the part, because obviously we don't experience and see little chunks of material spinning around inside a brick. So by this logic is how we develop the idea that tau xy is equivalent to tau yx. And we can just use one or the other to describe that stress state. All right, so that should be fairly familiar to you. And you should also remember this concept of Mohr's circle. So Mohr's circle is a way of visualizing how that stress element can be rotated such that we might find a more significant magnitude of stress. So at a particular location, it is convenient for us to have an axis where we can find a maximum stress value with respect to that axis. But it's certainly possible that the axes that we just happen to have chosen aren't necessarily the axes that the orientation that stress is highest at. Now, we don't really care about the stress in the orientation we chose. We care about the stress where it's highest, because that's what's going to lead to failure. So we have what's called 2D Mohr Circle, or how it's probably introduced as just Mohr Circle. And 2D Mohr Circle is about representing that stress state. So there is a vertical and horizontal axis, where the vertical axis is shear stress. At the top we have things that tend to make the block spin in a clockwise direction, and on the bottom, things that tend to make it want to spin in the counterclockwise direction. And the horizontal axis is normal stress. So we could have a block that has some amount of normal stress. I'll just draw it positive for now. And some shear stress. And again, I can just use tau xy here because tau yx is the same thing. So we can put that on there and say, all right, this is normal, a point which represents this side, which is the normal stress in the x direction, with a tau xy that tends to make it want to spin in a counterclockwise direction. So we can put, this represents a point down here where that stress is. So this is sigma x and tau xy. And another point up here at y, which is over here, and it tends to make it want to spin in a clockwise direction. So sigma y and tau xy would be that point. Now we can draw a line between these two, and of course they're going to cross the axis at some point here. And we can make a circle. It's a perfectly drawn circle. And what this circle represents is taking this stress element and rotating it about the z axis, the one that you're not seeing. So it's rotating it one direction or the other. And again, it doesn't matter too much, particularly what orientation it is. We really just care about the maximum stress. So it's possible to orientate this block such that all we have is normal stress. These are called the principal stress values. And it's possible to orientate this block such that all we have is shear stress. Again, stress is just force over area. So it's just just call it tau, because it's not xy at this point since we've got different planes. So this is normal stress, normal to the plane of that new orientation, and tau max according to some orientation. So Mohr circle, like all circles, is defined with two elements. There is a radius, r, and a center point, c. So the radius of any Mohr circle is, by Pythagorean theorem here, sigma x minus sigma y over 2 squared plus tau xy squared. And the center location of that circle is the average of sigma x plus sigma y over 2. So we can find some interesting values. So for example, we may want to know, let me draw a new one so I can clearly identify it here. We may want to know what is the values of our principal stresses. We'll call them sigma 1 and sigma 2. Or we may want to know at which point is shear stress maximum. Well, we can just take the center and the radius to come up with those. So sigma 1, let me say comma sigma 2, can be found by start at the center, sigma x plus sigma y over 2, and either go radius forward or radius back. So that is sigma x minus sigma y over 2 squared plus tau xy squared. And those will get you the principal stress values. Or we can want to know what the maximum shear stress and let me put a little caveat, I'll come back to this, maximum, which was just going to be the radius up or down from that center. So the maximum shear stress is sigma x minus sigma y over 2 squared plus tau xy. It's just the radius. And those principal stresses are going to be important, and the maximum shear stress is going to be important because we're going to have failure theories that are based on one or the other. One failure theory says when the principal stress is at the point where it breaks, it fails. Or another failure theory says when the maximum shear stress is reached, then it fails. So that's why we'll need to know what those are. All right, now let's move on to thinking about the fact that we don't live in a 2D world, we live in a 3D world. So even that stress element we drew before, we talked about rotating it about the z-axis, we started thinking about 3D cases. But in reality, we have potential to have sigma x, sigma y, sigma z, and your orientation doesn't really matter too much here. And we can have shear stress acting on x face in y direction, shear stress acting on y face x direction, y face z direction. So you put all these together and we have a 3D stress state. And as you'd expect, it takes 9 stress elements to describe this stress state. In the x face, on the x direction, would be normal stress, y face, y direction. Let me come back here. Z face, z direction. And then in the shear stress, we can have sigma xy, sigma xz. In the y face, we'd have y in the x and y in the z. And on the z face, we'd have z in the x and z in the y direction. Now, recall that when we looked at the 2D state, that's just this part of it, that these two, by statics, have to be equal. So tau yx and tau xz have to be equal. Otherwise, our stress element would spin around. The same thing happens to be true for everything on this diagonal. Yz must be z equal to zy, zx must be equal to xz in the shear stress. Otherwise, our cubical element would be spinning around. For most areas here, we're going to be looking at how components fail considering this 3D approach to stress state. So let's go back and look at Mohr Circle, and I'll draw that same stress state that we had before, where we take our xy and our shear stress. So this was tau in a clockwise, tau in a counterclockwise, and this is normal stress. And we had sigma x and sigma y that gave us some location, and from that we had a center and a radius, and we could find our sigmas, sigma 1 and sigma 2, and some, remember I gave that caveat earlier, the maximum shear stress. Well, now we could have orientation about a different plane. So imagine this like taking our cube, and instead of spinning it about the z-axis, we could spin it about the y-axis, or spin it about the x-axis. In fact, we could spin it about combinations of the axes and have any combination of these stress states. So it's possible that we have a sigma x, sigma z location, which might be down here and up here. Let me draw another perfect circle. And now we have a third principal stress. So as you can obviously tell from the circle, if we found the center between that two, so this is the actual maximum shear stress. So if we believed that this was our maximum shear stress and we went on a failure theory that said it breaks on maximum shear stress, we would have significantly underestimated. Now, for most of what we'll be doing in this class, we're concerned about plane stress. So because bending stress, or stress, normal stress due to bending, tends to be maximum away from the neutral axis. And because torsion tends to be maximum on the outside surface away from the center line, or the point at which it's twisting about, and because direct force, direct shear or axial stress tends to be constant, doesn't really affect our decision making, it's most likely that when we have some complicated loading situation, that what we care about is the stress element on the outside surface. So while that looks like a square, really we are talking about an infinitesimally small cube. And on the outside surface, if there's nothing pushing, there's no force acting down on this, then there can't be any force acting up from the materials to counteract that. For every action, there is equal and opposite reaction. So one of the stress states is always 0 in plane stress. So that's what we call plane stress. It looks like this, same like we were talking about 2D. However, we want to consider the fact that there is, in fact, a stress value there of 0. And it becomes important, and I'll show you why. So that's how xy. So we've got sigma x, sigma y, and some sigma z, which is 0. So if we go back to our Mohr circle, and we just did the 2D Mohr circle, we know that there is a value of normal stress and shear stress, counterclockwise, tau, clockwise, normal stress, that leads us to a local maximum for shear stress. We got our sigma 1s and our sigma 2s. Now, we also said that sigma z was 0, and tau in the zx direction, zy direction, however you want to look at it, is also 0. So we also have the yz orientation, and we have the yx orientation. So the actual maximum shear stress is found by looking in that 0 direction, different orientations. So we don't care so much about what these sub-max shear stresses are. We care about the absolute max. So the absolute maximum shear stress, the one that we care about for our failure theories, is going to be the difference sigma 1 minus sigma 3 over 2. As long as we orientate our sigmas, and this is just our principal stresses, this is standardized, that sigma 1 is greater than sigma 2, which is greater than sigma 3. All right, so that's how we find the absolute maximum. But how do you find those principal stresses? So, of course, you could do 3D Mohr circle the way we just described it, looking at each plane, looking at the xy plane, the yz plane, the xz plane, and yz plane, and find what those principal stress values are. Or if we know its plane stress state, we can find, using the Mohr circle equations, what's the maximum, what the two principal stresses are, and then we know, because it's plane stress, that the other plane stress value is 0. But it's certainly possible in a generic 3D stress state that we have non-zero sigma z. So if we have that situation where there is stress on the outside surface, say a pressure vessel is a great example, it's possible that we may need to find all 6 values of the stress states. So recall that those two values are the same. So there's a couple different ways we could go about doing it. I suggest using eigenvectors, the eigenvalues. And there's a link to a calculator in Blackboard where you can find what those eigenvalues for a 3x3 matrix are, put in your 3x3 matrix, and it will spit out 3 eigenvalues. And I don't have time in this video to go over how you come up with eigenvalues. It's just matrix math. Hopefully you've covered that in other math series. But what those eigenvalues are the roots of the equation if we solve a simultaneous set of equations, and those roots are our principal stresses. They won't be orientated necessarily when you solve it as sigma 1, sigma 2, sigma 3. Again, we'll just want to make sure that sigma 1 is greater than sigma 2, which is greater than sigma 3. Well, that'll about do it for this video. So what we've covered so far is the types of loading, the stress we can get from those types of loading, and how to find the absolute maximum at a particular point. Recall, where things fail, it's going to fail at a particular location, so we need to figure out where that location of maximum stress is, figure out the orientation such that we know the absolute maximum shear stress or the principal stresses, and from there we can actually start applying our failure theories. Well, until next time.